My name is Dominic Weber, and this presentation is about shortcut learning in deep learning models. To introduce this topic, we have three pictures, all of which are easily recognized as cows by humans. However, some neural networks will only classify the first one of these correctly. This poor result can be attributed to the phenomenon of shortcut learning, which is widespread in deep learning. And this is just one of countless examples that shows why this is such a huge obstacle in our efforts to improving generalization in deep learning. In this presentation, I cover 3 points. What is shortcut learning? What are the common sources of shortcuts? And thirdly, how do we counter these shortcut learning? I will focus on underlying causes and issues and challenges and evaluate solutions currently discussed in research. The paper by Geros defines shortcuts as solving problems by not learning the human intended solution. And this leads to the lack of generalization ability we saw in the cow example. Now, human networks use certain decision rules to perform their classification. Let this circle be the space of all possible decision rules. Then this subset is the decision rules leading to good accuracy within training. And this subset here leads to good accuracy in testing on IID data, independently and identically distributed data sets. But the actually desired solution is only a subset of this one. Solutions not covered by this inner circle are our shortcut solutions. And the ones we actually desire also perform well on an OOD dataset, an out-of-distribution dataset. Let's think back to the cow example. It is to be expected that a large proportion of training examples show cows in their natural habitat, a grassland background. And this is where the model performed well, but perhaps only because it associated this grassy background with the word cow itself. If the decision rules relied too heavily on this, we can see how it would fail to generalize to classifying cows on other backgrounds like the beach. Failures like this can have serious implications. For example, what about if this was a self-driving car that failed to recognize a pedestrian because he was standing in front of some fireworks? So we have seen that the generalization ability can be affected by this. The problem is that it can easily go undetected and then lead to unexpected and undesired solutions. This problem is not confined to image classification as such. It can be found anywhere, for example, in natural language processing and reinforcement learning, as we will see. Now, in image classification, it can affect the issues in two ways. Firstly, unintended superhuman performance. The image of this fox and this dog, for example, are still recognized as such by a particular neural network when the images are scrambled beyond human recognition. And we may have no practical uses for this ability. The second one being unintended subhuman performance. So this cat here is not recognized very accurately anymore by some neural networks when we remove texture information. But humans use texture and shape to identify images. And so we may want our neural networks to be able to do the same, which they can't here. Natural language processing. So in this example, the models were given claims and reasons, and they had to demonstrate correct comprehension by picking the correct statement that warrants this claim here, the correct one being the green one, warranting this claim. Natural language model BERT scored a 71% accuracy on this, but without having what the authors of the paper called the required world knowledge for this task. So how did it do this? It turns out it relied on simple cues, like, for example, the word not. This word was associated with the correct prediction 61% of the time and applies to 64% of all data points, which is why it works as a predictor, but this is not the intended solution. Similarly, reinforcement learning. This particular agent learned how to play the game of Tetris and came up with a winning solution. It first placed all the blocks as fast as it could, as this does accumulate some small amount of points. And then just before losing, it paused gameplay indefinitely. Here the objective functions were based on accumulating points. So this strategy in a sense succeeds, but it is not what a human would reasonably expect the solution to be. So what are the common sources of shortcuts? Models can develop certain inductive biases, and these biases influence how some solutions are much more easily detectable than others. The paper by Garros explains that once such a predictive feature is found, the decision rule may actually depend entirely on this shortcut feature. This is called discriminative learning. And what's the root cause? Four categories have been identified. The data distribution, of course, but also the model architecture and the way in which we perform backpropagation. Let's look at these. Loss functions. This here is the standard cross-entropy loss we know from classification problems, shown here for a distribution P and Q. Its derivative is used to adjust weights in backpropagation. But the paper by Jacobson argues that this provides no incentive to explain all the class-dependent aspects of the input. In fact, he shows on ImageNet data that one can manipulate the class-specific content of almost any image without changing the hidden activations. Let's keep this expression here in mind for later. Model architecture. In this classification example, the learner correctly identifies stars and moons on this blue IID test set, but only because these objects are in the same location within that black square as in the training data set. When the locations were changed, we have an OOD test set shown in red, and the learner failed to correctly identify them. Now, had this been a convolutional network, which is more invariant to object shift based on its localized convolutional nature, the learner would have been less likely to use this shortcut. However, convolutional nets fail in other ways. The paper by Baker states that the convolutional operations that occur at the earliest levels of convolutional nets are well suited to extract local oriented contrast, which explains this picture here of the aircraft, which is still recognized with a 16% probability when cut to pieces and overlaid on top of each other, but only a 1% probability when the edges are locally serrated. And it is this third picture at the bottom which is arguably much more recognizable by a human. Optimization method and learning rates. So stochastic gradient descent methods are common in deep learning. However, Arpit shows in his paper that they result in learning simple and generalized patterns before fitting more complex features. In fact, Lee shows in his paper that larger learning rates tend to cause learning simpler features. And this then is what causes poor generalization ability to occur, just like in this adversarial example, where the authors took an original image data set and modified them by adding a single predictive pixel. When they did this modification on the training set and the test set, the accuracy was large. When they only modified one of these data sets, the accuracy was close to zero. So the algorithm has actually relied heavily on a simple predictor here, a single pixel. So how do we detect shortcut learning? We have seen that detecting shortcuts depending on unexpected results is one way to do it, but this is not always feasible. It's not always so easy to do. So the paper by Ribeiro proposes a method which highlights certain pixel groups in a picture that have a positive weight towards a certain class. Now, if a model uses unintended features, we may have found a shortcut. For example, in this picture with the dog and the guitar, the first label is that of an electric guitar. This is not entirely correct, but it doesn't, these pixels don't lead us to believe that a shortcut has been used here, unless, of course, the location of this hand was used to arrive at that solution. Now, we can also modify the data and the methods themselves to observe possible changes, and then these could indicate shortcuts. And this ties into the question, how do we counter shortcuts? Well, an obvious starting point is is modifying the data. In this example here, the task was to classify between adult and child stick figures. Obviously, adults are taller, but in the training set, they also had less movement than children. So in the middle test set here, this is an IID test set. We have a very low error. When the authors went and modified the data to provide the adult stick figures with more movement in the test set, we now have this second test set here, which is an OOD test set, and the error has become huge. Remember the language model BERT and how it relied on the word no? Well, the authors also modified the data. They negated the claims and inverted the labels. And then language model BERT had an accuracy of just 53%. Same effect. The logical next step would be now to train with modified data. This is not always a practical step in real-life applications, but in this picture here, the authors trained a robotic arm to grasp objects entirely in a simulation environment. So this is a feasible option. They randomly varied camera position, lighting, object position, and textures. This is called domain randomization, and it worked. As you can see, the grasping location error reduced significantly on a real-life example. In other words, they have achieved real generalization ability. Next, disentanglement. Here we separate robust features from non-robust features. So models that perform well on adversarial examples, like the one shown earlier with the plane and the single pixel, tend to use more meaningful features for classification. And that's shown by this upper picture here of the frog. These are robust features, as opposed to this noise in the lower picture. So one approach is to filter out the non-robust features. And Ilias showed in his paper that this does lead to robust results without actually having to change the model itself. The downside is it relies on there being another robust and adversarially trained model already existing in the first place. Obviously, this is not always a given. Alternatively, instead of adding or removing data, we can also force models to take into account more of the available information that we do have. In other words, we modify the loss functions. So Jacobson, in his paper, he modified the loss function shown earlier. So now it has two terms. And basically, he treats these so-called semantic features and the nuisance features separately. The aim here is to reduce the impact or the information gained from the nuisance features, which correspond to the non-robust features in the top picture. Of course, this depends on actually being able to identify what these nuisance features are first. Now, I never told you how this problem here was solved. The authors introduced a so-called conditional variance conditional variance penalty. The algorithm basically paired images of the same class, just a small number of them, that had slightly different movements, as shown here on the two red boxes on the left. And it penalized exactly these small differences more than any of the other available features. And what this did was it based the prediction more on what they called core features, in this case height, and less on the style features like the movement. And interestingly, here it is not actually necessary to know what the style features are, because this regularization merely forces the use of features that do not vary much between objects of the same class. A related approach by Arjovsky describes their regularization term as a balance between predictive power and the robustness of the predictor across different training environments. So this is a balancing act. In conclusion, we have seen that neural networks often solve problems with unintended and simple features, and this does not generalize well to OOD data. The problem is caused by training data, the model architecture, and the way we do backpropagation. There are several successful methods for both detecting and countering this, but they may only be applicable to certain types of problems, and they may require further knowledge about the data set. One thing is for certain, as Gayros states, OOD generalization tests will need to become the rule rather than the exception. And now my concluding thought. Based on what was presented here today, shortcuts are not so much a mistake that occur in deep learning, but they are more an intrinsic characteristic and therefore a natural consequence of deep learning itself. As Ilias states in his paper, we should not be surprised that classifiers exploit highly predictive features that happen to be non-robust under a human selected notion of similarity. So we should not expect that they are both human meaningful and faithful to the models themselves. Thank you.